And it's the fact that classical mechanics had evolved as doctrines in this haphazard and opportunistic manner was the source of conceptual difficulties that bothered Harris. Okay. But now, this is a problem with the sort of form of the positivist answer to this, Michael's problem of rational conceptual development in science. The positivist translations of the famous thought experiment discussions into these axiomatic terms require that the behavior of rigid rods become more settled within this axiomatic framework than is plausible. Right? In other words, they were forced to freeze assumptions about ordinary matter into artificial fixity because those prerequisites have served as the stable core around which the theoretical they gave the kind of experimental data that the rest of the theory was supposed to organize. Okay. But just mathematically, when you do that, you lock mathematically within your axiomatics matters of conceptual advance in celestial mechanics to presumptions about ordinary matter on a localized scale. Okay. And you don't want to do that. Okay. In physics, the matter and how it interacts with the field is modeled opportunistically. We do not want to turn opportunistic forms of handling matter where you do not yet have a fuller story to tell. You don't want to be forced to turn it something that's a kind of a makeshift approximation and build it in and required to be actually a meaning postulate, part of a meaning postulate, in a theory trying to justify non-Euclidean, use of non-Euclidean geometry in physics. Okay. Anyway, that's just one way of stating sort of familiar complaints about the positivist program that you see in the space-time literature. Okay. But they make us, just the way Michael presented things, what does Michael Friedman want us to do? Does he want philosophers to dream up wrong-headed demands on physical theory, a la Mach or Poincaré, who both stated things that are not workable, in the hopes that someday a proper physicist will be inspired to make something good from our blunders, right? You know. Or are we expected to somehow work out theories of a perfection that is able to give a global theory of the sort that Janan was alluding to, where you can handle matter at a local scale along with cosmology all in one sweep? Right. Well, there's never been a theory developed like that. Now, these are just prima facie worries, and actually some of what Michael will talk about. There are many prospects in neo-Kantianism that do not fall into this particular trap, and I think that Michael's been thinking in that sort of vein. So I'm just sort of laying out, in the way things are presented in Dynamics of Reason, just because of history, you worry about this. Okay. That doesn't mean that there aren't other ways out. Okay. Now, what I'm going to do for the rest of the talk is kind of state how I want to look at these sorts of matter. And I'm focusing on getting rid of that view of axiomatic organization as the central thing that you want to be looking at. Okay, so that's actually why I said, even though the positivists naturally were led to the idea of making logical structure be the most important instrument of conceptual construction, that's exactly one of the issues I most wanted to target in my book. Okay. Okay. So much of my thinking in the book and some of the cases I report on are gentle forms of conceptual revolution, altering the definition of some term in a textbook or whatever. And usually this sort of detailed, nitty-gritty mathematical stuff is kind of viewed with contempt by a lot of historians of science concerned with big social movements and who funded you. But I want to know how, what happened with the notion of vector, stuff like that. Now, I think, despite the fact that these little shifts can be almost invisible, they exemplify critiques as concepts as meritorious philosophically as those exemplified within these splashier episodes like the great thought experiments in geometry. And actually, Hertz's worries about mechanics were eventually resolved by thinking in material science in the 20th century, largely by paying attention, very localized attention to how various terms were used in a localized context, and redefining them locally to fit those contexts. And then you could see the tensions between this application of force and its application over here. So it's actually moving from a solid to a fluid. Usually the notion of force shifts its meaning, its reference somehow. Okay. And that's what was bothering Hertz, actually. Okay. So what we want to do, look at, what I want to emphasize is the huge body of applied mathematics that tries to understand the reliability of localized reasoning techniques. And one of my complaints about people like Nancy Cartwright, they will point to surface anomalies in inferential behavior in physics. And they'd say, oh my gosh, there's some funny business going on here. Okay. There are more individuals in the modern university, in departments of applied mathematics, dedicated to studying and figuring out the reasons why you get those surface anomalies than there are philosophers, probably. Okay. And all that work is completely ignored. Okay. It does make these techniques rational, but boy, it's often hard to figure out why. It's incredibly subtle work. Okay. This is the kind of stuff I'd like to bring a little bit more into our sights as philosophers of science. Okay, and it's a fact that the most powerful inferential schemes employed within applied mathematics often prove erratic in their performance. That's why Cauchy was led to worry about how differential equations perform on the complex plane, and also his worries about the derivative and all that. And he was worried about some techniques in common techniques in celestial mechanics, where you develop a series, and sometimes you get wonderful results, and sometimes you get total mush. And the manipulations don't tell you on their face. They don't say I'm good or bad. They just give you numbers, and sometimes those numbers are really good, and sometimes they're awful. So this is the real nature of inferential, the problematic of inferential technique in science. You do not want to think of it on a logical model, a first-order model, where things don't go wrong like this. Okay. To understand these issues requires the applied mathematicians to develop what we need to call a picture of our computational place in nature. So there we are computing on a slab or a tablet, and there's nature doing whatever it's doing out there. We want to know when and why do those calculations give us good numbers about what's happening out there. What is the correspondence that makes it good when it's good, and what makes it fail when it fails? That's the kind of question that Cauchy began